Hello, my name is Mark, and welcome to Tutorial 2 of Dagster. That is the tutorial series where I'm introducing the parallel sat solver that I've coded with here at the ANU, and what it is and how to use it. So in Tutorial 1, we sort of talked about what is a sat problem, and the two broad paradigms, or at least two of them, which solve sat problems. So we're going to do a quick recap. So last tutorial we introduced sat problem, and we introduced two primary ways of going about it. So a sat problem was a classic computer science problem where we have binary variables and we have constraints that those binary variables must satisfy. We also talked about how the two primary ways of solving sat problems, that is the systematic backtracking search, particularly embodied in the CDCL or conflict-driven clause learning system. Additionally, we talked about stochastic local search, which was an alternative way of going about solving sat problems, which basically begins by assigning random values to variables and then flips those values to try and satisfy as many clauses as possible to solve the problem. Please review tutorial 1 if you're unsure about what a sat problem is or how CDCL and SLS work and what they are. Okay, so in this tutorial we're going to talk about a little bit about what Dagster does to parallelize the search problem process, and we're going to sort of talk about how Dagster is composed of many parts, and we're going to talk about those parts and introduce them at a high level and how those parts work together. So particularly the fundamental problem that Dagster is designed to solve is to try and answer the problem, how do we parallelize the process of sat solving? So in the previous tutorial we talked about systematic backtracking search, particularly embodied in the CDCL process, and the stochastic local search process, or SLS. And one of the things about those processes is that they are notably serial processes. Right, in the backtracking search, you, one stage at a time, choose a variable to assign a value to and then propagate the implications. Conversely, in the SLS process, you have one assignment to all the variables, and then you're flipping them one at a time. And this, of course, is wonderful for a serial processing architecture, but to take advantage of the parallel processing architecture that is most computers today, we want something that can actually do parallel process. So the question is, how do you take a sat problem and parallelize effectively the search over it? So there are two primary approaches that we will present in turn this tutorial. So basically, we have to break the problem up into parts, and there are primarily two ways of doing that. So the first of which is to break the problem into parts by making particular assignments to particular variables. That is breaking the problem into sets by cubes. Or we can actually partition the clauses of the problem and go about solving those partitions separately. Both of which we will present in turn this tutorial. So the first thing is breaking the problem into part by cubes. So if we take a sat problem and we make a variable assignment. So if we say we take the CNF and we say let variable 1 be true. Consequently, the search after assigning variable 1 to be true becomes quite different from the search after conversely assigning variable 1 to be false. So for instance, we can take the CNF and we can split the CNF into cases where variable 1 is true and variable 1 is false. And this basically breaks the entire search space into two disjoint spaces, one in which variable 1 is true, one in which variable 1 is false. And so what we can do is we can proceed by actually breaking the space into multiple sets. So, not just breaking on one variable, but then consequently breaking the consequent subproblems into further subproblems by assigning further variables. And in this way, we can basically turn one big problem into a whole bunch of subproblems, each qualified by splitting on a different cube, where a cube is a set of variable assignments. So we'll illustrate this. Anyway, so the resulting thing is that you have a whole bunch of disjoint spaces and you find solutions to each of those disjoint subspaces, and then that's the solution to the problem. So let's take an example. So in the last tutorial, we had a sat problem, which is given by on the left-hand side here, which is the exact same sat problem as in the first case, in tutorial 1. And then what we can do is we can take that problem and then we can proceed with solving that problem under the assumption that variable 3 is true. And that will result in a different problem than if we proceeded by solving that SAT problem with the assumption that variable 3 was false. So for instance, if we take the original CNF and we make the assignment that variable 3 is true, that assignment that variable 3 is true will satisfy some of the clauses and also unsatisfy some of the literals of some of the other clauses. Right? So for instance, if assigning the variable 3 to be true means that clauses index 1 and 2 are true, so 1 is true, or 2 is true, or 3 is true, is made true by the fact that 3 is assigned to be true, and therefore it's irrelevant to the processing of that cube, right? So, it's satisfied, great, we leave it as is. Conversely, the clause 5 or 6 is not influenced by whether we assign variable 3 to be true, so it propagates and is still relevant to subsequent search. Conversely, the clause not 3 or not 5, because 3 is assigned to be true, that is reduced to being a unit clause, not 5, which is obviously a hard constraint, and so forth and so on. So basically, what we do is when we take the original CNF and we assign a variable, that is, we cube the problem based on a particular variable, then we get a consequent CNF that is simpler in some senses, and that is a completely disjoint subproblem than what we would get if we assign variable 3 the other way. So for instance, if we take the original problem and we assign variable 3 to be false, then we note that some of the clauses become satisfied as a result of that minus 3, variable 3 being false, and other clauses get more constructed. So for instance, the assignment not 2 or not 3 becomes satisfied by variable 3 being false. Conversely, it's not then relevant to further processing on that problem, and so on and so on. So we have a reduced CNF and a reduced CNF by making the assignment to variable 3 either way. And then what we do is we can take those assignments, those CNF subproblems, and we can actually run a SAT process on them. Maybe one call will do that, maybe one process will do that on another in our multi-process system, and it will give us solutions. So for instance, if we say we take this problem, we assign variable 3 to be true, there is only one solution to the problem in which variable 3 is true, particularly 1 being true, 2 being false, 3 being true, 4 being false, 5 being false, 6 being true, is a solution to the problem that is unique, in this case, just by happenstance, after consequently assigning variable 3 to be true, and that is the unique solutions to this particular reduced SAT problem. However, conversely, by assigning variable 3 to be false, right, the resulting SAT problem that is reduced by that assignment can be solved, for instance, 3 ways. Well, actually, so we'll get to that in a sec. So, for instance, like this resolved SAT problem, this reduced SAT problem can be solved by assigning variable 1 to be true, variable 2 to be false, variable 3 to be false, variable 4 to be true, and variable 5 to be true. So, for instance, so 1 is true, so the first clause is satisfied. 5 is true, so the second clause is satisfied. 5 is true, so the third clause is satisfied. 2 is false, so that clause is satisfied. 5 is true, so this clause is satisfied. 1 is true, so that's, and so on. But one of the things that you notice, so for instance, with this particular variable assignment, is that it doesn't really, by assigning 1, 2, 3, and 4, and 5 variables, all of the clauses are satisfied, and it really doesn't consequently matter which way variable 6 is satisfied. So, conversely, all of the clauses are satisfied irrespective of the value of 6. So, we just leave 6 unspecified here. So this actual solution here represents 2 solutions, right? And then consequently, we have another solution. So 1 can be true, 3 can be false, 4 can be false, 5 can be true, 6 can be false, is a solution that satisfies all of the clauses here, irrespective of the assigned value for variable 2. Therefore, this here is a shorthand way of writing more than one solution. And like the last case as well, 1 is false, 3 is false, 4 is false, 5 is true, 6 is false, is irrespective of the variable valuation for 2. So in this way, basically what we can do is we can split the problem into different parts, depending upon the value of some variables. This gives us reduced CNFs, and we can solve those CNFs in parallel to produce solutions, which coincidentally are the set of solutions to the original CNF, right? Because nothing is lost here. And this is the process of breaking it apart by cubes. And this is one of the primary ways of actually doing parallel SAT, is to come up with a set of different variable assignments that are cubes, and then breaking the problem down into parts via those cubes, and then distributing the solving of the SAT problem via those reduced CNFs over many compute cores, and then collating the solutions of those parts across those cores to be the solutions to the original problem itself. So this is one way. Okay, so this is Mark in post-production. So one of the things that I also wanted to do is provide a bit of a graphical intuition as to what's going on here, not just looking at the clauses. So particularly one of the things you can do if you want to visualize this, for instance, is you can imagine the set of all possible valuations of all of the clauses as an area. So for instance, here I have shaded in an area. So this is all the possible valuations of all the possible variables. So this is like the unrestrained solution space. And what we can do is we can, in a certain visualization, we can say, okay, so for each clause that is added, that is for each constraint, an area of that search space is eliminated from being candidate solutions. So, for instance, like we can consider, maybe there are 1, 2, 3, 4 clauses that respectively eliminate this area here, and that area there, and this area here, and so on, and this area there. And then what happens is the remaining space is the solutions of the SAT problem. So particularly with this approach, so you can throw that into a SAT solver and it will respectively solve, that is, come up with solutions that more or less encode the white area that is not eliminated by any of the clauses. So what we do when we're doing the cubing approach, so for instance, let's say that we break on a particular variable. So in our example, we had breaking on variable 3. So for instance, we consider that the section of the solution space that has, say, 3 assigned to be positive as opposed to 3 assigned to be negative, might be visualized like so. So this here in the green is the space of the solution space that is not eliminated by any of the clauses, that happens to satisfy the constraint that 3 is true, for instance. And then what happens is when we throw that into the SAT solver, so this is like the set of all the clauses with the constraint that 3 must be true, then the respective SAT solver will give back respective set of solutions. That is, so all of the solutions will cover that space. So, this is solution 1, this is solution 2, this is solution 3, and 4, 5, 6, 7, 8. So, maybe the SAT solver throws back 8 solutions, which together, that is, the set of solutions cover that space. So that is the variables having the assignments that satisfy solution number 1 union with the set of valuations that satisfy solution number 2 union the set of valuations that satisfy solution number 3, etc., etc. Conversely, so this was the section of the search space where 3 was assigned to be true. And then we consider the disjoint side of the search space where 3 is assigned to be false. So instead of green, we have blue, right? And you can see that green and blue are entirely disjoint sets. When we throw, so conversely, then we throw into a SAT solver, find the set of solutions such that satisfies the constraints of the problem with the additional constraint that now 3 must be false. And then the SAT solver will throw back a set of solutions, solution 1, solution 2, solution 3, so on, that satisfy all of the constraints. That is specifically the constraints of the CNF with the additional constraint that 3 must be false. And so what happens is, from these two results, we have the solution set that corresponds with the first half of the problem, that is 3 being true, and then the solution set that corresponds with the second half of the problem, that is 3 being false. And then the solution set to the whole CNF, that is the entire solution space that is not in black, that is excluded by specific clauses, the solution set from the first half union with the solution set of the second half, right? That is the union of the space, that is satisfying either one of the first half of satisfying the solutions of the first half of the problem, or satisfying the solutions of the second half. So this is one way, but there's others. So one of the other ways that sort of appears is that what we can do is we can break the problem down into parts, not via cubes, but by actually breaking the clauses into subsets. Right? So we take, say, the first half of the clauses and we say to a compute core, okay, go and solve that. And then we take the second half of the clauses and we say to another computer core, okay, you go and solve that. Right? Now, this is a bit different than breaking it down by cubes, because when we do this process of, actually extracting a portion of the clauses in the CNF and giving that to a process, what it has is overlapping search space. Whereas, in the context of cubes, the resulting CNFs had a disjoint search space. In this case, we have overlapping. So let's give an example. So let's take the original CNF that we had from tutorial 1, and let's take the first half of the clauses, and we say that's partition CNF number 1, and we have the second half of the clauses, and we say that's partition CNF number 2. Now, if we actually run those through a SAT solver, basically each of those will actually generate a bunch of solutions. Notably, because these problems are smaller, they're actually less constrained. And then we have solutions to these two parts, right? And these correspond with the solution set that corresponds with the search space of the first half, and the solution set that corresponds with the solution space of the second half. And then consequently, we can do an intersection. So let's take an example. So in this case, we take the first half of the clauses, and that creates partition CNF number 1. And we can throw that into a SAT solver and get a series of solutions for that part of the CNF. So for instance, if we assign variable 3 to be true, variable 5 to be false, and variable 6 to be true, then that will satisfy all the clauses. So clause number 1, 1, 2, or 3, 3 is true, so that's satisfied. 3 is true, so the second is satisfied, 6 is true, so the third, 5 is false, so the third, so the fourth, and then 3 is true, so the final one. So that actually satisfies all the clauses. Conversely, 2 or not 3 or not 4 or 5 also satisfies all of the clauses, and so on and so on. We can do that to the second half of the clauses as well, the second partition CNF, and we can run those through a SAT solver to get the solutions. Now, the solutions to each part of, for each partition CNF, form a solution set for those clauses. And what we want is we want solutions to the whole problem. That is, solutions that satisfy the first half of the clauses and also satisfy the second half of the clauses. Right? We want the solution set, the set of solutions that is encoded by the solutions to the first half and the solutions to the second half. And the way we do that is via intersection. Right? So, for instance, like the variable valuation 3 or not 5 or 6 is compatible with the variable valuation 1 or not 2 or 3 or not 4, right? There's nothing that prohibits those from jiving together, compatible, right? But conversely, 3 or not 5 or 6 does not jive with 2 or not 3 or 4 or 5, right? Because 3 can't be assigned both ways and 5 can't be assigned both ways either, right? So some of these solution sets actually have a positive intersection, and if we scan through those compatible solution sets, we can pull out the solution to the original problem, right? And this actually is correct solution to the original problem. So this is an entirely different way of breaking the problem down into parts and then resolving those parts together, such as you might be able to do in a multi-process parallel environment, right? So then there's sort of the question of, well, how do you, in the same way as with the cubes, what variables do you break the problem down by? In this case, it's, well, what subsets of the clauses do you partition the CNFs by? And so these are two generally quite broad ways of solving the problem. So I also wanted to highlight this process of search space partitioning with the graphical model. So, as before, if we consider that there's, an unrefined solution space, that is the set of all possible valuations of all of the variables, as this big white space here, we can consider the set of clauses that might be disjoint. So, for instance, we have two sets of clauses. So this one here eliminates that portion of the search space from being solution, and that portion of the search space from being solution. And also then we have a second set that eliminates this space of the search from being a solution, and that space of the search from being a solution. right? So in this case, we have two partitions of clauses. So these clauses eliminate those sections of the search space, and those clauses eliminate those sections from the search space. Now, obviously, the true solution to the intermix of those clauses will be the union of the search space not excluded by either of them. So we can see this space intersecting that space equals this space. And then, the ideal to try and find solutions to that. So for instance, particularly via this process, we throw into, so we have partition one of the clauses and we throw that into a SAT solver, and then the SAT solver will return the set of solutions that characterize the space not excluded by those clauses. So the solution to the first part of the problem, this first partition of the CNF, returns solution 1, solution 2, solution 3, solution 4, solution 5, 6, 7, 8, 9, 10, as the solutions return to the first part of the problem. Right? Conversely, the second half of the problem, so the SAT solver returns the solution space to that. So solution 1, solution 2, solution 3, solution 4, solution 5, solution 6, 7, 8, 9, 10. Now we have a solution set for the first half of the problem and a solution set for the second half of the problem, and this is with the partition of the clauses. Now we know that the solution of both of those clauses together is the intersection of both of those solution spaces, right? So this is particularly the space that is not excluded by both sets of clauses. So this is the solution set for the first intersection with the solution set of the second, right? So we can actually overlay where the yellow area is the intersection of the solution set of the first and the solution set of the second. Now the language becomes a bit confusing here because the way we do this, right? So we iterate over the solution set of the first. So this is solution number 1, and there is obviously no intersection with the solution set number 2, and then we have solution number 2, no intersection, and then we have this one here, right? So say we have this one solution from solution set 1 that does have a positive intersection with some of the solutions of solution set 2. So if, for instance, now the way to represent this, so let's say we have solution 1, which consists of, so 1 being positive, 2 being negative, 3 being negative, 4 being positive, 5 being negative, for instance, like 1 or not 2, or 1 and not 2 and not 3, or 4 or not 5, is the solution 1, and then let's say we have an intersecting solution number 2, right? That is 4 and not 5, and 6 and not 7. So the intersection of two solutions from two different solution sets is the union of the literals, right? So 1 and not 2 and not 3 and 4 and not 5, and 4 and not 5 and 6 and not 7 is 1 and not 2 and not 3 and 4 and not 5 and 6 and 7. So there's an overlapping language, right? We're taking the intersection of solution spaces, which is pairwise over all of the pairs of solutions for each of those spaces, where the intersection of them is the union of their literals. So you can see how this is a bit confusing. So why I was kind of motivated to make this note in post-production. Okay, so just an annotation as well. From feedback, some people kind of confused about what these elements of the diagram represent, particularly how intersections might intersect, or the union of their literals. So when I talk about a solution, so let's say this is, as per the previous example, this is like solution 1, and then like we're from solution set 1, and then this is the solution from solution set 2, which has a positive intersection shown in yellow. Right. So the idea is that when we're talking about a solution, what we're talking about is a solution involves multiple or potentially multiple valuations to the variables. So for instance, if we take, as per previously, the solution 1, let's say that is the valuations 1, not 2, not 3, 4, and not 5. Tacitly, that solution involves or includes all the possible valuations of the variables not specified, right? So 1 and not 2 and not 3 and 4 and not 5 tacitly includes, the case where variables 6 and 7 are both positive or true, and, when they're both negative, and when one of them is positive. So that includes 1 and not 2 and not 3 and 4 and not 5 and 6 and 7, 1 and not 2 and not 3 and 4 and not 5 and not 6 and 7, 1 and not 2 and not 3 and 4 and not 5 and 6 and not 7, and 1 and not 2 and not 3 and 4 and 5 and not 6. That's supposed to be not 6 and not 7. Right, so you can see that solution 1 involves a whole bunch of solutions, right? So it actually spans a space of possible full solution full solution variable sets of the problem. So it's actually, if you think about it, maybe like each of these little cells, are representative of, more atomic solutions. Anyway, and then we have, say, solution 2, which, as per previously, might be evaluation of, 4 and not 5 and 6 and not 7, which tacitly includes, all of the valuations over the variables 1, 2, and 3. So that's, 1, 2, 3, 4, not 5, 6, not 7, not 1, 2, 3, 4, not 5, 6, not 7, blah, 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 blah. So there, you can see that in these cases, these solutions 1, solution 2, include a space, and there's actually, between the two of them, there's actually in this case, a singular solution, right, that is compatible with both, right, that is in the intersection of the both of them, right? So in this case, it's really straightforward. It's the 1, not 2, not 3, 1, not 2, not 3, where is that? 1, not 2, not 3, and then 4, not 5, 6, 7 is the only solution in this case that is the compatible between solutions 1 and solutions 2. That is the intersection shown in yellow. Broad ways of solving a problem. Now there's another one that's sort of an intermix between them, right, where what you do is you decompose the problem into two parts, like you take, partition of clauses part 1 and partition of clauses part 2, and then what you do is that you generate the solution set for the first partition set, for the first CNF, and then you use those as constraints on the second. So let's take an example. So let's take the original CNF that we had in tutorial 1, and let's break them down into two parts via partition. So we have partition CNF1, partition CNF2, and then what we do is we run the first part, the partition CNF number 1, into a SAT solver, which then gives us the solutions to the first partition CNF, like so. And then what we can do is we can say, okay, we're basically saying, are there any solutions to the second partition CNF that are compatible with the solutions that we generated to the first half? Right. So basically, what we do is we take each of the solutions to the first half of the CNF, and then we actually run it through a copy of the partition CNF number 2. So, for instance, the partition CNF number 2, not 4, 5, 6, 1, 2, 4, 3, 4, 6, not 4, 5, 6, 1, 2, 4, 3, 4, 6, etc., etc. And then what we do is we append the solutions of the first CNF as unit clauses on the running of the second. So we're running a copy of the second CNF with the unit constraint 3, not 5, 6, which is the first solution to the first. So if there are any solutions to the second CNF, the second partition of the CNF, that are compatible with the solution to the first half of the CNF, 3 minus 5, 6, then that constitutes a solution of the problem, which coincidentally there is. So, for instance, the first solution to the first partition of the CNF, 3, not 5, 6, actually resolves with the second half of the CNF, the second partition CNF, to form a solution to the total problem, 1, not 2, 3, minus 4, minus 6. That's actually a solution to the actual whole CNF. Right, and then conversely, the second solution to the first half of the CNF is compatible with the second half of the second CNF of the problem, to form the solution 2, not 3, not 4, 5, not 6, and so on and so on. Now note that, for instance, not all solutions to the first half of the CNF actually are compatible with the second half of the CNF. So, for instance, 1, not 2, not 3, 4, not 5, 6 is a solution to the first half of the CNF, but if we actually adjoin that via unit clauses to the second half, there is no solution. In any case, this is sort of an intermixing, because what you're doing is you're cubing the second half of the CNF via a solution to the first half of the CNF that you got via partitioning the original CNF. So it's sort of a bit of an intermix. And this is another way of parallelizing the process. You pick a part of the problem, and then you solve the second half in relation to the first.
Okay, and also from completeness, I thought I'd also give a graphical intuition of the third kind of approach. That is specifically, solving the first part of a problem to generate solutions that then consequently act as constraints on the solving of the second half of the problem. So particularly, what we can do is we can, in a graphical sense, as before, we have the space of all solutions. That is every possible valuation here represented as a pictographic area. And then we can consider, say, we have subproblem 1 and then subproblem 2. So in this sense, what happens is, we take subproblem 1 and we throw that into a SAT solver, and that generates solutions, and then we take each of these solutions in turn. So let's consider that this here is solution number 1, right? And then what we do is we take that solution number 1 and we make that a set of constraints, particularly unit constraints that must be satisfied. So that is the set of constraints that is entirely that area that is solution number 1. And then what we do is we apply that together with the constraints of subproblem 2 to be solved. So it's particularly the intersection of satisfying solution number 1 and satisfying solution part 2 is this area here, which then we pass into a SAT solver, and then the SAT solver gives the solutions that correspond to the intermix of those constraints. And so the idea is then, we repeat this process by choosing a different solution, say this one here, and then we repeat the process, generating an area intersecting with the second part, gives another solution, and we proceed iteratively until we actually describe the set of spaces that is the intermix of the constraints of the first half of the problem together with the second half.
Now this is like basically brought over line of 3 different processes to actually parallelize the SAT problem. So it's breaking down by cubes. We have simple disjoint searching. The solutions are either and or. We have disjoint via clause subsets, where we have parallel solving on different clause partitions, and the solutions are the union of the solutions of the partitioned CNFs. And then we have another process which is kind of an intermix of the both, which is breaking a problem down by sequence, right? We are cubing the seconds by solutions to the first that we attained by partitions of the original problem. Now, Dagster is sort of the logical extension of this sort of logic, right? So what we're doing is we're breaking parts of the problem via subsets and partitions, and then we're solving different parts of the problem via sequence, and also by mixing and the union by normal things. So the idea is that what we have essentially a directed acyclic graph. So we have a whole bunch of different sub-problems to the CNF. So this is breaking clauses of the original problem down by partitions. And then we've also specified the order and the way in which those are resolved together, so those solved together. So for instance, let's take an example. So this here is an example of a CNF file on the left here. So we have 6 variables, 8 clauses. And then what we have is what is input into Dagster, which is a DAG file, right? So in this case, we have 6 different subproblems. That is, we have partitioned the clauses in this CNF into 6 different parts, right? So particularly, so in this here we've got clauses. So we have subproblem 0 consists of the clauses indexed 0, 4, and 6, right? So 0, 1, 2, 3, 4, 5, 6, right? Those clauses constitute subproblem 0. And then we have, subproblem 1 is clause index 0, 1, 3, 4, 6, is the same as last time except with the inclusion of clause 1 and clause 3. So the subproblems don't actually have to be entirely disjoint from each other. It's not a partition necessarily. So subset clause 5 is, clause index 2, 3, and 7. And so when we have all of these problems, subproblems, we've got 6 different subproblems indexed 0 through 5. And then what we have is a specification of the way that those subproblems are solved together. So for instance, we can see from the graphical representation of this DAG on the right that the solutions to subproblem 0 consequently constrain subproblem 1. So that is, for each solution that comes out of subproblem 0, function as unit clauses on a running of subproblem 1. That is solution in sequence, right, which we described here, right? This is a solution in sequence. Subproblem 1 generates solutions which then constrain the running of subproblem 2, which generates solutions to that. So this is great. So what we have is we have a connection from subproblem 0 to subproblem 1. And we also have a notation here, right? So what we're saying is the solutions of subproblem 0 then consequently constrain the runnings of subproblem 1, and particularly we're interested only in the variable valuations for variables 1 and 2, right? So all of the solutions to subproblem 0, particularly the variable values for 1 and 2, get passed on as constraints to the solvings of subproblem 1, right? Conversely, the solutions to subproblem 2 get passed on as constraints to the runnings of subproblem 3, and the running of subproblem 5 then altogether act as constraints on subproblem 4. So what happens here is we have a three-way join. So this is similar to what we said previously, where we had to do an intersection of the solution space. So we turn back here. There we go. We had solution subproblem 1, solution subproblem 2. We had n-way intersection. Equally so here. We have solutions for 5, solutions for 1, solutions for 3, n-way intermix, then seed runnings of subproblem 4. Right? And then at the end of the run, what we have the variables of the whole problem that we're interested in, particularly variable values 1 to 6, which will then be the output of the Dagster program that we're primarily interested in. So this is actually the inputs that go into the Dagster program. Particularly, there is a CNF problem. That is a CNF file. And we also have a DAG file. This is an appropriately formatted DAG file, which specifies the subproblems that there are in the CNF and the way in which those subproblems are going to be solved together. Parts in sequence, parts simultaneously, and then what Dagster does is it takes these inputs and then it figures out how to solve that in parallel across multiple cores. So, kind of like, we can kind of visualize this process going on, right, where we have, different parts of the problem. So, maybe subproblem 0 is really hard and emits solutions really slowly, which will then hold up the processing on node 1, right, on subproblem 1. And then what Dagster is doing is it's allocating different workers to work on different parts of the problem to generate solutions on the fly, right? And the idea is that at the end of the day, as these solutions get funneled through the DAG, then the results of, the solutions of subproblem 4 with the constraining inputs that are given into it actually then are solutions to the whole problem, right? And we have essentially a parallel flow. So, particularly, I'll show you how this works. So just give me a moment and I'll actually show this input. Okay, so what I'm going to do is I'm going to show you how to compile Dagster and how to run it with a specific input. So in the case of the example just given, so we have the CNF respectively. Maybe I'll see that, maybe not. And then we have the same DAG as file. So it's mycnf.txt, mydag.txt, and this is Dagster source code folder. So what we can do, so we have all of the source here, so clear, ... and then what we do is we make. So now Dagster is being compiled a sec. Or we can just speed this up by just going to make J8. It's just using multiple processes to kind of speed up the process of compiling Dagster. All right, and then now we have Dagster directory. So Dagster, right? Blah 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 blah. And it says Dagster. You need to provide a DAG and CNF, which is what we're going to do. So, like one of the things that we have is we have. So the first thing is so Dagster is a process that uses MPI. So we need to do MPI run is the MPI run command, and we need to specify how many processes we're going to use. So MPI run N2, so it's 2 processes. One of them will be master, the other one will be one worker. And then we need to give MPI run the executable. And then what we need to do is, per the instruction, we need to give it the DAG file. So it's my dag.txt, and then the CNF file, my cnf.txt. All right, and then what we do is when we run that, chonk, 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 and Dagster's finished. Now that was what we can do. Now the default output is /dag out, so we go cat /dag out, dag.out.txt, and boom, they're the solutions to the problem. So cat my cnf. This is the problem. Those are the solutions. Now like this is, it's like that's how you use Dagster. Amazing. Now there's a bit more to it than that. So what I'm going to do is I'm going to try a bit more of a complicated example, right? So I've got another CNF here. So where is it? This cat my problem.cnf. Right. So this is a bit more intense, right? So it's a big CNF, right? It's a much more involved thing. So this is actually a pentomino problem, which there's also a solver in there for that. So, and then there's cat my problem.dag, right? So this is much more impressive problem. And so what we're going to do, so we could just directly pipe that into Dagster. So we could just go Dagster, and then this is my problem dag. We could go my problem.cnf. Right, we could do that, but I will do that in a second. What we're going to do, so I'm going to show you a utility inside of Dagster that sort of visualizes the process of Dagster actually solving this thing. So inside of run scripts, you can see some examples of run scripts that is just executing calls for Dagster, and particularly we want to output some environment variables that more or less tell Dagster where to put and what level of logging we want. So particularly we want log level v3, and then we want to log to standard error. So when we run MPI run Dagster, right, with my problem.cnf, my CNF, we've got a CNF output, and then std out.txt, and then we want to pipe the standard error.txt, right? And so what that will do is that will run Dagster with log level 3 outputting the logs to standard error. Now if we run that, what we'll do is it'll just dump a whole lot of logs to that. So we're going to go python as viewer.py. I just want to show you this thing because it's kind of fun. So viewer, it says, all right, give me a DAG and give me your thing. So it's my problem.dag, and then /ter. There you go. I was like, ooh, there we go. Plus, zoom in a bit. And then we can actually see the worker working. So it's working on number 8, and now it's working on problem not 8, 7, and now 8. And it's like, oop, there we go. Solution process. Anyway, so the basic idea of this thing here is that you can basically see when you initialize a Dagster run, you can have this viewer utility that actually visualizes the process of Dagster actually solving the problem. Like this is the parallel worker working on this part of the problem, and then working on that part of the problem, and then working on another part. And so it shows you that together with a visualization of the DAG itself, and then it also gives you basic statistics of like how many messages were input, how many messages were output from each of the nodes, and also the average time that it took, to find a solution, to prove that it was satisfiable, or otherwise to prove that there were no more solutions, and then basically tells you information about master, so the master processor. So yeah, a Dagster has
Okay, so just inserting a note here. particularly what a pentomino problem is and how it's generated and how it is solved and how it is decomposed, is a topic of next tutorial. So tune in next time if you're interested in that. But yes, back to tutorial.
Right, and so what we can see is that we can run Dagster like this, and like actually see how the input is into Dagster, and we can actually see in very direct sense the way in which Dagster is solving these things together, right? Like actually in real time, which is kind of nice, right? So what Dagster has is it's got a bunch of workers. And it's basically what it's doing is there's a master process that's sort of coordinating what work needs to be done, and then there's like a whole bunch of different workers, and the master is telling each of the workers, what part of what subproblem to work on, and particularly with what message generated from the previous work in the DAG to be working upon, right? And the master process is sort of coordinating the workers and telling them what to do and when. But it also has like a storage of the work that needs to be done and the work that has been done, right? So that's sort of the center coordination point of the system. And this is sort of, pretty common, multi-process scheme. Very simple. Right, so basically what master says, it's like, hey, you, worker 1, work on node or subproblem A with an incoming message B, that is a constraint from previous nodes, and report back solutions to me. And then the worker says, it's like, oh, okay, master, here are the solutions X, and then Y, and then Z, and then there's no more solutions. I'm done, right? And then master says, okay, well, all right, thank you for that. Like here's some work to do on a node B with incoming message C, etc. And basically this iterates. And then master keeps track of all of the work that is done and all the work that needs to be done until there's no more work to do, at which point the problem has been solved. Right, and we can kind of see this like essentially in the previous example, we can sort of see like the master's eye view of the work. So we have subproblems, in this case, 0 to 8, and then we have 3 workers that 4 workers that are allocated to subproblem 1, 2, and 4. And each of them are ingesting messages from other subproblems and seeding work to other subproblems as well. And this is the GUI that you saw previously is more or less the master's eye view of this process of coordination, which is kind of cool. Anyway, so one other thing that we note about Dagster is it's not just a master and then a whole bunch of identical workers that are all doing CDCL, although that certainly is an option in Dagster, but Dagster is sort of a bit of a tool that has a lot of bells and whistles. And one of the configurations of the whole Dagster system is that different workers can have helper processes, right? So this is not just master and workers, but master, worker, and helpers for those workers. So particularly, one of the types of helpers that are included in the Dagster system are a whole bunch of SLS helpers. So the worker runs essentially a CDCL process, which is systematic, and it is also aided by one or many SLS processes that are running the same problem. Additionally, and we'll get to this a bit later, there's also an optional strengthener process where there is a separate process that tries to strengthen the learnt clauses in the CDCL process that the worker is running. Anyway, we'll get to this in turn, but first things first, SLS helpers. So, there's many configuration options in Dagster, and we will get to most of them in the next tutorial, but one of those configuration options is the presence of SLS workers. And we will get to the configuration of it, but at this tutorial we're just doing the high-level stuff. Okay, so how do the CDCL workers and their helping SLS cooperate? So the first thing is that when the master says to the worker, okay, work on this subproblem with that message, then the worker says, okay, let me try and find solutions, but it'll also pass it on to the helper processes, the SLS. Now there's different ways, particularly too, in Dagster, that those SLS processes can actually help solve the problem that master gave it. So the primary one is that the helping SLS processes can actually find solutions to the problem itself. Because SLS, stochastic local search, is a genuinely different paradigm of search process than the CDCL that the worker is running. And in some cases, the SLS can actually be faster. So the SLS can find solutions to the problem that the worker has. The other one is that, and this is a bit more esoteric, the SLS processes can pass suggestions to the CDCL, that is the worker process, of what variables it should be selecting. So if you remember from tutorial 1, when we had, the CDCL process needs to make variable assignments, that is choosing a variable and what assignment to give it, valuation to give it. And the SLS process has the option, it is an option, of passing back to the worker CDCL process hints on what variables the CDCL should be branching on. So what happens is, particularly because the worker has multiple helper SLSs in most cases, what it does is it sets the SLSs to be working on different parts of the problem themselves. So as we will see. So for instance, the SLS, the CDCL process that the worker is using is a branching backtracking search, as we explored in tutorial number 1. And what happens is each worker has a set of SLS helper processes that the CDCL allocates to them. It says work on the problem at this depth. And the idea is that, in this branching tree structure that is the SLS, there are different depths in the search that the worker can say to the CLS, okay, I want you to work on the same problem I am, but I want you to work from this point in my search space. So, for instance, this might be variable 1 is false, variable 2 is false, variable 3 is true, variable 4 is true, variable 5 is true, variable 6 is false. And the worker says to the SLS, work on the problem, but don't go outside of those bounds of the variables that I have assigned at this point in my search. And so what happens is that sort of functions as a prefix on the SLS solution process for that specific helper. And then, the CDCL proceeds by making a sequence of other variable assignments and then allocates that as a prefix to the other SLS and kicks it off at that depth, and then so on and so on. So the idea is that each worker has a whole bunch of SLSs working on the same problem as it is, but at different depths in its process. And the idea is that the SLS, the CDCL, actually chooses the SLS process that is closer to its own search space as a source of variable suggestions. The idea being that if the SLS is flipping a particular variable often, then that's a good candidate for the CDCL to choose as a variable for its selection. So this is sort of like, just one way in which, the master says to the worker, work on this problem. The worker says to the SLS, work on that problem as well, just at different depths in my search. The SLS problems can report solutions back to the worker, which then funnels back to the master. Or the SLS can also report the variables that it's often flipping at the different depths of the CDCL process, and then the worker gets to choose which variable assignments from those SLSs it wants to actually do in its own CDCL search. That's the impression. So the other one is the other element in the system is the strengthener. So the worker is a CDCL process, that is, it's learning clauses as it's solving the process. And what happens is that when the CDCL process is learning these clauses, it's also learning clauses in response to the clauses that it's already learnt, right? And then over time, older learnt clauses can become stale or less influential. And the idea is that, essentially the part of the search space that the learnt clause prohibits becomes multiply covered by other learnt clauses. So the idea is that there's a separate process called the strengthener, which basically tries to take a learnt clause and then try and strengthen it. That is, pop literals off the learnt clause that aren't less necessary in order to actually make the learnt clause stronger. So the idea being that when, in the last tutorial we saw that a learnt clause was a singular cut in the implication graph that led to a contradiction, as the CDCL process proceeds, increasingly it is the case that not all of those variables no longer need to be assigned in order to reach a contradiction, right? So the strengthener proceeds by popping various variable literals off, and insofar as it can do that and still lead to contradiction every time, then the learnt clause is valid. So it passes back reduced and simplified clauses to the worker. Now, the configuration of multiple SLS workers, particularly like what depths the SLS the worker should allocate the SLSs to be working at, and what depth increment there should be, particularly if the SLS should be giving suggestions to the worker, if there is a strengthener, and how those things are all configured together, form this part of this system that is Dagster that we've designed, right? And there's a lot of configuration. So just summarizing that, remember from last lesson that learnt clauses block implication chains that lead to contradiction. As more learnt clauses are added, more potential implications are added, and older learnt clauses can then become overdetermined. That is, yep. And so the solution for the strengthener is to scan the older learnt clauses for the redundant literals, that are those which, if they were not asserted, would still lead to a contradiction now, and then remove the redundant literals, returning to a CDCL worker a stronger clause. Now, there's another element in the system as well. So the master process has multiple workers, and those workers have multiple SLS work helpers and or strengthener workers. But there's also the configuration of the master system, right? So the master has a store, or it's not only just got an algorithm that it uses to allocate work to workers, but it also has a storage of some sense of what work needs to be done and has been done. And particularly, there are two different ways that master, so as it has been coded, can store, receive, transmit, and eliminate work. So particularly, one of the most basic, is just directly to store, in a very dumb sense, all of the work that needs to be done and has been done. So we call this the table solution. So this is these are the assignments, to and from node 1 that have occurred, right? And then this is the work to be done, in a big table. And the idea is that, in this way, it's just a very simple way of master keeping track and keeping tabs on what work has been allocated to what workers, what work needs to be allocated, that is solutions from those workers that need to be subsequently processed, and the like. And this has, particular advantage. It's obviously quite simple, but it is also not particularly elegant in terms of what it's doing, because there's better ways. So the alternative is it can, instead of just storing these things as big lists of variables, it can actually store them in a more logical format. So particularly, what we want to do is we want to a more logical representation of a union of these assignments is a binary decision diagram, right? So this is a more logical representation of a list of assignments, and it's also more logically compact, right? So one of the weaknesses of the table solutions method is that as the solution proceeds, because there's no simplification in the work that master is doing, right? It's, these things can overlap or intersect or just explode exponentially, right? So for instance, here we have 1 minus 2 minus 3 minus 4 minus 1, 2, 3, 4, blah, blah, blah. This is all the permutation, almost all the permutations of 1, 2, 3, 4 that you can have. It's just an exponential explosion. So using the table solutions method for master is very fast and simple, but it also has the drawback of potentially being explosive in terms of memory requirements. But whereas the alternative configuration for master is using BDDs to represent the work that has been done and needs to be done, and that is much more memory compact because it is much more logically compact. The primary drawback of this, being that it is more complicated because master has to, pull apart and simplify this logical representation. But conversely, it has a smaller footprint. And another side effect is because master is using this logical representation, there is actually some logical simplification that can happen. So particularly in the previous case, where we had a table where we've almost got all of the permutations of variables 1 to 4 as work to be done, right? That can just be directly simplified by, we have, what is it? It's 1 minus 2 minus 3, and then plus or minus 4 can just be simplified by popping the 4. Right, so we have a smaller message that encodes basically the same information that we could have generated if we had some simplification in the table solution method that would naturally be part of the BDD. Anyway, so this is like yet another option for another part of the Dagster system between storing work and coordinating work as tables versus storing work and coordinating work as binary decision diagrams. So, in summary, there's a whole bunch of different bells and whistles that Dagster can use. So Dagster is a master worker architecture, and one of the primary configurations is, well, how many workers are there? Additionally, there's, because master is a coordinating process, there's, the means, the algorithms, and the way in which master is storing, accessing, using, modifying, the work that has been done and needs to be done from all of the workers, particularly table and BDD storage. There's also the question of, well, like how many SLS helpers does each of the workers have, right? And how are they configured in terms of, are they reporting solutions, and particularly, are they actually giving variable suggestions back to the worker CDCL? And then secondarily, there's also, do the worker processes have strengthener processes as well, right? And these are like all the various different ways in which Dagster has configuration. Now, in summary, we will, like in the next tutorial, we will dig down into the details of some of this configuration because there's a lot. And as in the worked example, I think I showed you the wizard that is the configuration and all of the options for these things. We will get to that more in the next session. But I just wanted to finish this tutorial with a, kind of like a summary. Do these configurations make a difference? And the answer is yes, they can, sometimes. And we're just going to present a small case study example where, yes, where the workers have SLS processes, this can make a difference. So particularly, like case example, we're going to talk about costas arrays. Now you might ask, well, what is a costas array? And I will tell you. So a costas array is basically a grid, n by n grid, where each of the columns and or rows are filled in. Like so. So this is a 6 by 6 costas array. And what defines a costas array is essentially two primary conditions. That is that there is a filled-in box for every row and column, and that the displacements between any 2 points is unique. Right. So for instance, like if we take, this here, it's 2 down, 1 to the right, and we will notice that there is no other pair of points that is 2 down, 1 to the right between any of them. So this is, or for instance, like this is 3 up, 2 to the right. There is no other pair of solutions here that actually satisfy that. So a costas array is a grid n by n where there is a dot for every row and column, and the displacement between any 2 dots is unique. And that's a costas array. Now, costas array is a combinatorial problem. It's quite obviously combinatorial, or at least pretty difficult. And there's been some work over the years to try and find these things. And I think currently unknown, there's like 31 and 32. They don't know if there's any costas arrays of that size. It's sort of the limit of what we know. Anyway, so costas array is just a classic case example. And the idea is that what we can do is we can obviously encode this in SAT. And then what we can do is we can, perform some very, very basic decomposition. We say, okay, so for the first half of the problem, it's just, find the dots in the first 3 columns, that satisfies the constraints that are relevant to that. And then the second half of the problem is just solve the rest of the problem. So particularly we can have a 2-stage DAG where we have 2 subproblems, the first being solve for the first 3 columns, and the second being solve for all of the columns, where, the connection between the first subproblem and the second is the variable valuations that constitute the first 3 columns of the problem. So particularly we can see that this is actually, I think it's a 5 by 5. It's pretty small. Anyway, and we're interested in reporting at the end of the run, the values for all of the columns and the rows. So particularly as it's a 5 by 5 costas array, we're interested in all of the values 1 to 25. Right, no worries. Now if we basically, do this problem, so I'll show you how to generate this thing. Okay, so now I'm going to show you how to compile a costas problem using Dagster. So the first thing is you probably have the Dagster repository. It looks like this. There's a couple of directories. And inside one of the directories, there's the benchmarks directory. and we have a whole bunch of benchmarks, one of which is costas, cd costas, boom, like so. And now costas, so this here is make clean. So this is like a C program that generates a costas CNF. So go make. So it's now, just give it a sec, it's compiling the C program that generates the costas CNF. And then we have generate costas N. So basically it tells you how to use a thing. So we're going to generate costas N, dash N. This is the size of the costas array we want. So we're going to go something small. Let's go 7. Yeah, 7's good. And then if we just do that, what it'll do is it'll spit to the standard output the CNF. So we want to costas 7.cnf. And then what it'll do is it'll also spit out a mapping file to the standard error stream, which just tells you what each of the variables mean. Costas 7.map, let's say. And there we go. So what happens is now we have costas 7.cnf, costas 7.dag, and costas 7.map. So we can go cat costas 7.cnf. Take a look at it. That's what it looks like. Cat the dag file. The dag file looks like that. So we have the first 3 columns, as we saw previously, and that's the dag that corresponds with that. And then what we can do is we can just basically run that using Dagster. So we go mpi run -n2 //dagster/Dagster. So this is pointing to the Dagster directory. /costas 7.dag costas 7.cnf. Run, and that'll boop. There's our solutions. So this is the full log because we set the environment variables previously to point to standard error. So that's the actual solutions of the problem. Right? We'll go cat dag out.text. Those are the actual solutions to the costas problem. We go wc -l dag out. I think there's 200 solutions. There you go. And those are also symmetry broken solutions. So that's an example of how you solve costas problem using Dagster. So inside, just for note, inside of the benchmark directory, there's a whole bunch of different generators for different types of problems, which we can probably get into in the next tutorial, or maybe. But yes, so that's just showing you that. Right, and we can see, basically how Dagster can be used to solve a costas problem. Now, basically what we can do is we can, ramp this up, and then what we can do is with this particular problem, we can sort of fiddle around with some of the bells and whistles and knobs. So, for instance, like, do we want the workers to have strengthener processors? Yes or no? Like, do we want, how many SLS helpers do we want per worker, etc. And one of the things that we can do, we can also fiddle around with the decomposition. So, in the previous slide we had, say decomposition via the first 3 columns, but we could also experiment with, say, decomposition via the first 2 columns, which would then partition the problem, more coarsely, or with the first 3 columns would partition the problem more finely. And we can see that that has a profound difference on the solving qualities of the costas array problem. So this here is a graph from a paper which was published presenting Dagster to the Pacific Rim International Conference on Artificial Intelligence, pre-K. So it's like Dagster Parallel Structured Search Case Studies, pre-K 2022, forthcoming with authors. And so this here reports the runtime performance of Dagster computing all of the solutions of various costas arrays of sizes 10 to 15. It's like a log scale y-axis. And we have a comparison, right? So if we just use TinySat, which is a single serial process to try and do the same problem, that's this red line here. So we can see that we're actually beating TinySat, which is good. We're using parallel computing to actually speed up performance. Wonderful. We notice here that we have 3 sets of 4 lines here, right? Where the top line here is 3-column decomposition, and the bottom line here is 2-column decomposition. So, as previous, we could either break the problem down by the first 3 columns or by the first 2 columns on the first subproblem. That actually, that whether we do that 3 or 2 actually has the effect of how finely broken down the problem is for parallel computing. And, the finer we break it down, the slower the parallel overhead becomes, which is the primary solution determinant of the solution time for this. So, for instance, if we take 10 by 10 costas arrays, it's a relatively easy problem. Ideally, we don't want too much parallel overhead because it's going to be relatively fast, so 2-column is actually faster. But conversely, if we go all the way out to 14 by 14, which is much bigger, then having a more finely ground decomposition is better, because relative to the solving time, the parallel overhead is smaller. Now, the point of this graph that I want to draw your attention to is that what we have is, for each of these colors, we have green, cyan, blue, and black. I tried to make it a bit of a gradient. We have different options. So, for instance, we have notation C, which is just the workers being CDCL. We have CL, which is the workers being CDCL with one associated SLS worker. Then we have CSL, which is the workers being a CDCL. We have a strengthener and we have a local search helper procedure. And then we have CS, which is just the CDCL and the strengthener, but no assisting SLS workers, right? And we can see here that the presence or absence of these helpers actually does make a rather large difference on the solving time, or can, at least in the counting of Costas arrays. And so this is just an example where like one of the benefits of the Dagster system is that we have this singular tool with all of these knobs that you can fiddle with, right? Basically to experiment and find performance where you want. So maybe just running Dagster with CDCL only is better in some cases, and maybe running it with strengthener is better in others. And the idea is that within the Dagster configuration, it's easy to switch from one to the other to try and find or experiment around with what works. Right, so this is just one of many case studies yet to be presented in Freekai. But just want to draw your attention to one of the principal virtues of Dagster, which I just said, that Dagster allows easy-ish parallel experimentation. Right, so not only can you just fiddle around with different possible decompositions via DAGs, so you can change the DAG input to change the variables, or to change the number of subproblems, or to change how those subproblems are arranged. But there's also a whole lot of configuration options as to what workers there are and how those workers are configured, CDCL, SLS, and or strengthening processes, with a whole bunch of configurations. And so that's sort of like the principal demonstration of Dagster. Now, I feel like this tutorial 2 is probably a bit more conceptual. So in the next tutorial, basically what I want to actually do is I want to actually go through the process of what it's actually like to turn some of these options off and on. In this tutorial, we're sort of at the high level described the components of the Dagster system and how they relate. Now I'm actually going to show you in tutorial 3. So keep your hats on. Anyway, see you later.